In this video, we're going to begin our discussion with estimating a population proportion. So we now discuss inferential statistics, the process of generalizing information from a sample to a population. We will study two areas of inferential statistics in this class: estimation, that's where sample data is used to estimate the value of an unknown parameter, such as p or mu, and hypothesis testing. So this chapter we'll deal with estimation, and in this section we'll be dealing with estimating a population proportion. So, quick reminder, a statistic is a numerical summary of a sample. A parameter is a numerical summary of a sample proportion. The point estimate is a value of a statistic that estimates the value of a parameter. The point estimate for the population proportion is p hat. Now this should look familiar to you. This is what is referred to as the sample proportion. Okay, let's take a look at a quick example. So in July of 2008, a poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. Of the people surveyed, 1,123 were in favor. Obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So p hat in this case, that is going to be equal to 1123 over the total, 1783. To 3 decimal places, this is 0.630. Now, keep in mind, if it asked for the people who were against this, it would be 1783 minus 1123. That would be 660 over 1783. So be careful and make sure that you read the problem carefully for this. All right, with this point estimate, you might guess the proportion of all voters who are in favor of the death penalty is approximately 63%. Did we get every single registered voter? No, of course not. The point estimate may be incorrect. To account for this error, you might want to adjust your guess by stating the proportion of voters who favor the death penalty for persons convicted of murder, give or take 0.04 or 4%, which is what is referred to as the margin of error. This would create a range or interval of values. So if we did this 4% margin of error, it would look like this, because it could be plus or minus 0.04. Doing each of these separately, so asked how confident you are in the proportion is between this and this inclusive, you might respond, I am 70% confident that the proportion of voters nationwide who are in favor of the death penalty for a person convicted of murder is between this and this inclusive. Now, if you want an interval for which the confidence increases to say 90%, what do you think would happen to the interval? Would the interval be larger or smaller? Well, when you create this, you want your point estimate, which in our case is p hat, which is 0.630, to be right smack in the middle. Okay? A lower level of confidence will get you a smaller interval of values. A higher level of confidence will get you a greater interval of values. So in general, as the percent confidence increases, the interval of values would also increase. So a confidence interval is an interval of numbers based on a point estimate for an unknown parameter. The level of confidence is the expected proportions of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted by 1 minus alpha times 100%. So in other words, it's going to be a percent. So it could be 90% level of confidence, could be 95% level of confidence. All right, so in our death penalty example, the 0.590 to 0.670 is the confidence interval. And I've written it on the side here. Now keep in mind, 0.590 is part of the interval, and so is 0.670. In the death penalty example, 70% was the level of confidence. So a 90% confidence interval implies that if 100 different confidence intervals are constructed, each based on a different sample from the same population, then we would expect 90 of the intervals to include the parameter and 10 to not include the parameter. So confidence interval estimates for the population proportion are of the form of the point estimate plus or minus the margin of error. So let's do an example to show a 90% confidence interval with a specified point estimate. So I'm going to draw this now below. So now I've drawn 10 different confidence intervals. Notice the 9 that are in black each contains the point estimate, which is p hat, which is 0.630. Notice the one in red, the confidence interval I've drawn, does not contain the point estimate here. This would be an example of a 90% confidence interval. And again, as a quick reminder, the margin of error is going to determine the width of the confidence interval. Okay, so we can express the results of what I just did in a different way. Whether a confidence interval contains the population parameter depends solely on the value of the sample statistic. Any sample statistic that is in the tails of the sampling distribution will result in a confidence interval that doesn't include the population parameter. And this is the picture that is drawn below to represent that. Now, you see this z sub alpha over 2. That is what is called the critical value of the distribution. It represents the number of standard deviations the sample statistic can be from the parameter and still result in an interval that includes the parameter. Think of it as your boundary value. If it goes to the left or to the right, it's probably in the tail, which means it's not going to be included. Now, when we draw this accordingly, okay, let's say the 90%. Let me draw that here below. There is the thought process, right, with a 90% confidence interval. The 90% is in the middle, and then keep in mind, you have 10% that is left, but you have to split them up evenly into the two tails. So that's 5% and 5%. So now I'll draw the 95% and the 99% below. So some of the common critical values would be with a 90%, a 95%, and a 99%. Okay? It shows the area in each particular tail, and then the critical value for this. Now, I don't expect you to memorize the table. Okay? I'm going to show you how you can put any of these particular values into the calculator. So if I want to figure out what the critical value is going to be, it's going to be an inverse norm problem. So inverse norm. And let's start with the 90%. Now again, at the very end of the 90%, and we go to the left. 90 plus 5 is 95. So I can write that as a decimal of 0.95. Here, the mean is going to be 0, and the standard deviation is 1. All right, I will show you how to put that into the calculator quickly now. Okay, so second and vars go down to inverse norm, which is number 3. We would put in 0.95, hit enter. The mean's already 0. The standard deviation's already 1. Highlight, paste, hit enter. And rounding that to 2 decimal places, that would be 1.64. But here I'll end up putting it to 3 decimal places, rounded appropriately. So for 95%, that would be inverse norm 0.975, comma 0, comma 1. Rounding that, that's 1 and 96 hundredths. And then 99%, that would be inverse norm 0.995, comma 0, comma 1, and to 2 decimal places here, that would be 2.58. Okay, so how will we do an interpretation? Okay, you would put in a level of confidence that the population proportion is between whatever the lower bound and the upper bound is going to be. So a 90% level of confidence means that 90% of all possible samples results in confidence intervals that include the parameter, but also means it's 10% of all possible samples result in confidence intervals that don't include the parameter. Caution. Okay? A 1 minus alpha times 100% confidence interval does not tell us that there is a 1 minus alpha times 100% probability that the parameter lies between the upper and lower bounds. That is not what it's telling us here. Okay, let's do one example with this. So USA Today Gallup poll asked 1,006 Americans how much it would bother them to stay in a room on the 13th floor of a hotel. Interestingly enough, 13% said it would bother them. The margin of error was 3% with a 95% confidence. Write an interpretation of these results. Okay, so remember, it is what? The point estimate plus or minus the margin of error. So it's 13%, I'll write as a decimal, plus or minus. We have a 3% error, that's 0.03. So I'll separate. Right. So my confidence interval would be this. And then I'm going to write the interpretation now for this. We are 95% confident that the population proportion of adult Americans who would be bothered to stay in a room on the 13th floor of a hotel is between 0.10 and 0.16 inclusive.